Okay, so we have started recording, so I think we can kick off this event properly. So many of you will know this is one of the very last events of Leeds Digital Festival 2022. In fact, I think it might well be the last one. I'm not sure if there are any others going on this late this evening. So it's been a couple of weeks of highlighting the various sort of technological sort of developments taking place in the region. And this is more of that, with a specific focus on the work that's happening in the University of Leeds. So all the sort of people that you will hear from today are employees of the university. Actually, with the exception of me, everybody here is relatively new to the University of Leeds as well. So it's great to sort of have these guys on board and sort of hear more about what they've been working on in this sort of area. So my name is Faisal Mushtaq. I am the co-director for the Center for Immersive Technologies. And I'll very, very quickly talk you through what the Center for Immersive Technologies is and what it does and some of the sort of history behind that. And then we'll get on to our set of speakers for this evening. Some of you will have seen the email that was sort of circulated giving a bit more detail about the presentations, but I will also introduce them ahead of time. So let me get going on my share screen. Okay, hopefully you can all see that. So as I mentioned, the Center for Immersive Technologies, the University of Leeds, it is a cross-institute or cross-faculty research center. And what that means is that it brings together academics from various different specialties and different schools who are all contributing to the world of immersive technologies. Now, the thing to know about immersive technologies, we're going to have a specific focus here on virtual reality, but it's a whole spectrum of sort of new technologies ranging from augmented reality, where you can see the world and have it sort of augmented with digital information, through to virtual reality, where you might be in a sort of head-mounted display and everything around you is digitally created. So virtual reality then, it's going to be a specific focus of much of our talks, I think. In fact, all of them will cover the VR side of immersive. Virtual reality is in fact sort of a very old phenomenon, sort of 60s or so. It's the very first set of systems that came out. And for those of you who have perhaps sort of been around this sort of world for a while, will know that the world of virtual reality seemed to be sort of taking off in a very big way in the 1990s. But it didn't quite sort of fully mature at that time. It didn't quite sort of get the full adoption that was anticipated and expected from industry at the time. And there were many reasons for that, but I want to highlight one specific reason, one specific contributor to that. And this here is a very technical sort of slide here. I don't want to sort of abstract away. Let's not focus too much on those sort of details, but essentially a whole bunch of experiments, fundamental sort of research on the visual response to virtual displays and the sort of the way in which your eyes sort of responded to sort of virtual environments compared to the real world is fundamentally sort of different. There's a sort of issue called a Virtuous Accommodation conflict, which we'll be happy to sort of expand on in this sort of discussion. I won't go into it in too much detail right now, but it's one of the factors that caused sort of eye strain and headaches at the time, contributing to the sort of low levels of adoption. And in fact, some of this work was actually developed by a colleague of ours who's now who's the founder director of the center, Mark Williams, and this is his PhD supervisor over here. And Mark and John, this is John 1, part of their PhD, part of Mark's PhD, identified some of these fundamental sort of issues, which caused quite a storm at the time when it was published, causing some of the virtual reality companies, some of the companies that were invested in virtual reality at the time, to proceed with sort of a legal case against the university at which they were doing this sort of research, which was a very interesting sort of turn of events. Now, of course, it didn't go to anything because the science was sort of sound, but it did demonstrate the power of fundamental research to change the landscape of VR. Now, fast forward sort of 20 odd years later, and virtual reality is kicking off again in a sort of a way that is fundamentally different in scale to that in the 1990s. And this is an image. This is just so happens to be one metric for the advancement of virtual reality systems. This is the megapixels per eye in a virtual reality system. And you can see this sort of exponential sort of growth here, kicked off around about in 2015 with the Oculus Rift DK1. This is a big turning point in virtual reality that you sort of see today. And around about this time, when sort of virtual reality sort of started to see big investment from the sort of tech companies again in the mid sort of sort of 2015 or so, the University of Leeds and sort of Mark, who happened to be here now, were approached by various companies to have a look at the visual sort of response to virtual reality systems. And then we sort of undertook a couple of sort of studies. One of those was funded by the BBC, which ended up, as you'll sort of see here, making headline news in The Guardian, which demonstrated that there were some potential issues with using VR from a sort of a physiological sort of perspective, particularly in young children. And this is a small sort of pilot study, but it sort of corroborated sort of their evidence from other sort of studies around the sort of world, and ended up sort of creating quite a sort of a furore, I guess, in the virtual reality world, and set the University of Leeds up as sort of with this sort of notorious sort of reputation here as people who didn't quite sort of want to see AR and VR sort of succeed, but really couldn't be sort of quite sort of so in fact quite the opposite. We are big proponents of virtual reality and immersive reality, immersive sort of technologies more broadly. And then this is why in 2019, we launched the Center for Immersive Technologies, because we felt it was sort of incumbent on us as people who have been around this sort of world for quite a while now, to undertake, or at least sort of position our sort of a team and sort of the sector as a whole on focusing on critical, ethical, and responsible research in immersive. And since 2019, we've been doing this in a multitude of ways. We have specific sort of priorities. I won't go through those in too much detail. You're going to be hearing from our speakers about specific sort of case studies within this sort of center. But I will just highlight some of the sort of work that has taken place very, very briefly. We have, some of you who have been sort of in the university or visited the University of Leeds will have seen this sort of spaceship looking object. It's a Virtuosity driving simulator, which is used to assess and to help develop sort of artificial sort of intelligence for driving. It's to do sort of research on how sort of drivers interact with sort of pedestrians and cyclists, and has been really sort of influential in shaping some of the sort of transport regulations within London on HGV sort of windscreens and pedestrian safety. That's one particular sort of example. We also have been using these systems. Some of you who might have young children will know all about Minecraft. And we've been using Minecraft in virtual reality to help sort of make decisions about city planning in a more democratic way than is currently sort of taking place, having more stakeholders involved in that sort of process. So that's another potential use case for immersive realities, which is transforming the way that we make decisions in the local and national government. We also have been using augmented reality and virtual reality for connecting people with sites of sort of a cultural relevance. We have projects on virtual Holocaust, working with the Anne Frank Museum in the Netherlands, and working with numerous sort of museums here in the UK. And then a big sort of area for us has been on sort of the applications of augmented reality in the operating theatre. So the University of Leeds has a very strong relationship with Leeds Teaching Hospitals Trust, and we have been implementing these technologies, particularly for sort of neurosurgery in daily sort of surgical practice. And then I will just very quickly, so coming down sort of full circle from our sort of Guardian article, we've also been using virtual reality to help train and sort of educate and assess children as part of a very large sort of longitudinal birth cohort study called the Born in Bradford project. And I'm pleased to sort of say, to sort of really come full circle on some of that earlier work that we did in 2017. We are starting a new project in November, which is going to be looking at the ways in which we can design virtual reality systems to mitigate adverse after effects of exposure in children and other sort of specific sort of populations. So all of this work that has happened, all this research, and you'll be hearing much more about some of this in more depth very soon, has led to the University of Leeds and the Leeds City region more widely being recognized as a sort of powerhouse for immersive research and development, which we're sort of very proud to have contributed to. And times are sort of very exciting at the university. We are currently in the process of refurbishing. If many of you know sort of the University of Leeds campus, you might know the E.C. Stoner building, which is where the School of Computing used to be. We are currently in the process of refurbishing that space for XR laboratories and XR classrooms. And we also are about to install the UK's largest omnidirectional treadmill, which you'll see here in these architect drawings. So very exciting times at the University of Leeds in the immersive world. And you're going to hopefully hear a little bit more about the future of immersive research at the university and beyond through our set of speakers. So with that introduction done, I would like to pass over to our first speaker for the evening, who is Dr. Ryan Moorhead. And Ryan joined us from Harvard. I think that was just before the pandemic really hit home, and we all went into sort of lockdown. So it feels like Ryan is sort of new, although in reality, I think it's what, 2.5 years maybe. I've completely lost track of time now with the pandemic, so many people have. So Ryan joins us from Harvard and was previously a PhD student at UC Berkeley. And Ryan has been doing some really fascinating work as the co-director of the Immersive Cognition Lab at the university on virtual reality and virtual sort of display technologies. So I will hand over to Ryan, who will talk to you about how he has been pioneering the use of virtual realities for the human movement. So over to you, Ryan. I think your screen is showing. Perfect. So I will mute myself and then feel free to take over.
Yeah, great. Yeah, so I'm Ryan Moorhead, originally from America, and went to undergraduate through graduate school and postdoc there. And now I'm a lecturer at the University of Leeds in the School of Psychology. And what I study is human movement, and I try to figure out essentially how people become really good at making movements. So we've started to use virtual reality as a tool to do this now that the pandemic's over. And with my background, I come from laboratories where we use very high quality motion capture equipment to quantify human movements. But with the Immersive Cognition Lab, what we're using is virtual reality, which I'm sure most of you are more or less familiar with this. There's head tracking and hand tracking, and the critical idea with virtual reality is that the user has a display that shows them something. And so the typical kind of task that we would do here is have somebody sit down at a table and reach for different targets. And hopefully this clip is not too choppy. It is actually kind of choppy on my screen as well. So what's happening here is there are targets descending in the workspace, and the participant can reach out and intercept them. And we have people do this, and it's very similar to the kinds of tasks that we would do with much more sophisticated, much more expensive equipment in other movement science labs. So when I came to the University of Leeds, I wanted to know, is this virtual reality technology that we're using actually good enough at measuring movements? And this became a project of one of our PhD students, Matthew Warburton, And here you can see a schematic from his recent paper that shows what's going on in the background with virtual reality. To record a movement, when you move the actual controller, which you can see over here on the left, the computer does a bunch of stuff, and eventually you see what movements you made on the screen. And what we're doing in Matthew's project is actually measuring how much time elapses between your movement and you seeing the actual feedback in the world. So what Matthew did, and this is a pandemic project, he did this in his house in Pudsey, I believe, and he got his desktop computer, hooked it up to the VR system. He mounted the virtual reality system's controller in a vise, and he slid that vise back and forth on a linear guide, so it was always making really consistent movements. Matthew did this with a variety of virtual reality systems such as the HTC Vive, Oculus Rift, Rift S, and the Valve Index. Then he took his smartphone and recorded both the image on the screen inside the headset of these VR systems and the motion of the controller. And he came up with a really clever way to relate the motion on the screen to the motion of this controller by rapidly changing the colors of the screen inside. And this is a video. Hopefully you guys can get some sense of what's going on here from this. It's not too choppy over Zoom, but he made these movements in the dark, and the movement of the controller was matched with a little white LED, and the controller screen or the heads-up display screen would flash different colors as it moved back and forth. And what you could do is go in and analyze these videos and look at the cross correlation between the activity of the headset screen and the motion of the LED in space. And what we found from this was that all of these different systems had actually pretty low latencies. The slowest was the Valve Index. We ran these at different refresh rates that had about a 40 millisecond latency. The fastest was the original Oculus Rift down at 20. This is all for sudden movements. And this is an important factor here, because when you move the controller in a virtual reality system, it actually starts to predict the motion that you're making. And so what that does, by predicting your motions, it's able to reduce the effective latency down to 12 milliseconds or less across all of these systems. And you can actually see this when you plot the difference between the real motion of the controller and the virtually recorded motion of the controller on a graph. You can see that the virtual position actually stays for 25 milliseconds, stays still before the motion prediction catches up. And the general thing, I mean, it is the case that there's a short delay here before the motion prediction catches up and the VR system knows where you are. But if you look at the overall movement over the first 300 milliseconds, which is very fast, they're actually very close to corresponding. And the general position that we take in this paper is that virtual reality systems are actually very, very good as movement science tools. And we think that they're so good, actually, that they're probably going to supplant a lot of much more expensive motion tracking systems for a lot of laboratories around the world. Okay, so this equipment, virtual reality equipment, is very good. It has high spatial and temporal accuracy. So what do we actually do with it? Well, often we'll have people come in and sit down and they'll just make movements, sort of like what I was trying to show you with the video earlier of people intercepting targets. They have a little start position where they move, where they initially put their hand and they reach to a target, just like I'm doing with my mouse cursor right here. And then what we can do is just plot the path that their hand takes. And a general concept in movement science is that you never make a perfect movement. As you make the same movement again, there's variance in exactly where you go. And if you keep reaching repeatedly, you won't ever see the exact same thing every time. So what we do is take this position data and we break it down into kinematics. And all kinematics is taking the position of the controller and looking at the change of it or some other metric like that over time. And we can go in and look at different kinematic markers like peak acceleration, peak speed, or peak deceleration, which correspond to these locations on the actual hand paths in space. And we can use these to analyze the movements. And one thing that we look at is variability over time. So if we are looking at something like where is peak deceleration or where is peak speed, we can look at the spread in these dots and quantify that to tell us something about movement. So we do this regularly. We do it for kind of esoteric scientific reasons and that I won't get into, but there's also more practical applications. And so in a new project that we're just getting started, we're looking at quantifying movements with virtual reality for movement disorders. So an example movement disorder is cerebellar ataxia, which is you get damage to the cerebellum either because you have a genetic disorder, you had a stroke, or you had some sort of traumatic brain injury. And what the word ataxia means is that you're not able to walk anymore. And you can kind of see an example of a lady that has ataxia here trying to walk. Her gait is very abnormal. She's having a lot of problems. She needs help from the doctor while she makes these movements. And it's not only walking that's impaired in cerebellar ataxia, but also other types of movements as well. Here I'm showing reaching. So here she's just trying to simply touch her nose and then reach out and touch the pen tip of the doctor. And she's wobbling a lot, having a lot of issues in flight as her hand's moving and that sort of thing. So what we're doing in this task is developing actually a battery of tests that normally a neurologist would deliver to somebody, and we're embedding them within mini games so that a child, because children get cerebellar ataxia, can come in and play our game. And in the example that I'm showing here, they just move their controllers around to scoop up these green nanites, and over time the pink nanites, which are the bad ones, jump onto their controller. And it's their job to shake the controllers and make the bad nanites fall off. And by looking at the kinematic traces, the kinematic data for what happens when they're trying to shake these controllers, we can actually develop a subtest from that's equivalent to what a neurologist would give them with looking at a similar type of movement in the clinic. So what we imagine down the road is that we can develop tests like this with virtual reality and then eventually augmented reality. And just like today, the Apple smartwatch can detect a fall and maybe detect that you're having a heart attack and automatically warn you. It may be the case that at some point in the future, virtual reality or augmented reality glasses could automatically detect if you have a movement disorder such as cerebellar ataxia or Parkinson's disease. And with that, I'll just like to thank the labs, and that's the end of my talk.
Fantastic. Thanks very much, Ryan. That was very interesting. So feel free to post questions in the chat if you would like to ask for any additional detail on any of the sort of points that are being made. But I will just very quickly ask you, Ryan. So you mentioned here about sort of detection of potential sort of problems, but I wonder in some conditions where perhaps there's also the possibility of training, do you also see that as a sort of potential use case for virtual reality? So I'm thinking of sort of stroke rehabilitation and other sort of movement difficulties where retraining of lost motor skills is needed.
Yeah, so there are a bunch of cases where the retraining and getting better at a movement skill is definitely an application of VR and XR. In the case of movement disorders, most of them are degenerative, and so people will not really get better over time. It's one of the really sad things about these movement disorders. However, what we could do is actually quantify if they're trying to do a new medicine or they've started exercising or something like that. We can quantify whether that's actually helping them or not, and that's one potential use of this technology. In the case of stroke rehabilitation, it is possible that by repeatedly making certain movements, especially just the general thing is actually that engaging people and having them use their arms or use their legs again after a stroke, that's really critical. And that's where virtual reality, because it's so engaging and dynamic, can be really useful.
Mm-hmm. Yeah, thank you. That's really interesting. I just wonder on this sort of distinction, you also mentioned, well, perhaps in the future, you might also be using augmented reality. So is that another potential use case? Is that where training might be sort of more useful? You can interact with the real world?
Yeah, absolutely. I mean, right now the problem with augmented reality is that it's very limited, and you know, the ones that work the best are using a phone or an iPad, like, or something like that. But in the future, we think there will be glasses that you can use, and that automated computer vision based hand tracking will get even better. And so, yeah, in the case, I mean, I can imagine somebody using augmented reality to train them to do something like ride a bike, or I don't know, drive a car, something like that, and it might be able to give tips and pointers and point out where you're having some issues that you might not have noticed, and essentially act as a coach.
Mm-hmm. Yeah, that's very interesting. I like the bike example. Someone who learned to ride a bike as an adult, I can tell you how difficult that is, that process, and certainly could have benefited from having some glasses telling me what to do. Yeah, so and some of the sort of conversations I've been having with, in fact, people over the course of Leeds Digital Festival, people working in the industry are telling me they're very confident that Apple will be releasing at least one product in this sort of space in the next sort of 12 months or so. So that's something to sort of watch out for, and that might potentially be a point which sparks more development in this area. Fantastic. Thank you very much, Ryan. So we will move on to our next speaker. This is Dr. Carlo Campagnoli. And Carlo has also joined us from the US, but he's originally from Italy. He took a little detour to Princeton and Brown prior to that, where he did his PhD, and then Princeton postdoc. And Carlo is a vision scientist, and he's going to be telling us, he's got a great title. In fact, there we go. My mind is saying, let's go. My brain is saying no. And this, in fact, relates to some of the fundamental research that Carlo was doing in Princeton with Dr. Jordan Taylor on implicit and explicit biases. So I'm going to hand over to Carlo. And Carlo, please take it away.
Hi, so I'm guessing that you are seeing the presentation full screen now.
Yes, yeah, I can see that clearly. Yeah.
Okay, so just 1 second. Hi, so thanks again for the invitation. That is great to be here. And hi everyone. I'm Carlo Campagnoli. I'm a faculty member of the Immersive Cognition Lab myself at the University of Leeds. And today I wanted to talk a little bit about this this idea of like the experience of being immersed in virtual reality and sort of what that means for the research and development of the VR technology at large. And really, in hindsight, the title should have been slightly different to include like to be conscious and subconscious 3D biases in VR, because that perception in particular is something that's going to be at the core of this whole presentation. And the big challenge basically that I want to address in this presentation here is really this idea of like how do we define the realism? So it's basically the R part of the VR of the VR acronym there. What does it really mean to be for a virtual environment to feel realistic, and how do we act? How do we interact as humans when we are immersed inside it? And this challenge for the development of virtual reality as well as augmented reality, XR, and all this kind of technology, goes back to problems that are very old. So even more than 1,000 years ago. So Alhazen was aware of this, and then later on in the Renaissance, Leon Battista Alberti was developing some sort of technology that would allow artists and architects to basically do all the beautiful things that they did in those ages. But really the main question here is what is the, even after all these years, after all these centuries, we're still sort of struggling, or at least we're still studying what is the best technology that gets us to the same level of realism that we experience when we are in the physical world, because there are many differences between when you are in a virtual environment relative to when you are in the physical world. And the problem with addressing the notion of realism and trying to get to improve the realism, the impression of realism in virtual reality is the fact that as much as we try to have better and better technology, better and better computer graphics, and improve the computer power and all these kind of things, that perception at the subjective level remains something that really is a different experience for each one of us, which is kind of akin to, it's in philosophical terms, it's like a qualia, in the same way that color perception is subjective. So we might agree on a verbal level that something is red and something is green, but that doesn't really tell us what red and green feel like internally inside of each one of us. So there's this level of agreement, conscious level of agreement, that we all share, and it allows us to communicate and interact. But then there's an implicit, more subconscious level that we don't have access to, and we don't know whether it's the same or not. And that perception is kind of the same. It's kind of the same in many ways. There are also some differences, but we don't really know. We can agree on a behavioral level, essentially, that we experience the same level of realism and 3D-ness, if you will, but we don't know whether it means the same in the internal representation that we have of the physical world. And just to give you an example from empirical experience, a few years ago, I ran this experiment where we built this augmented reality equipment that was allowing us to project holograms behind a reflective surface. So that was a semi-transparent mirror behind which you could, on top of the hologram, could superimpose also physical objects. So it was kind of like, it was AR in the same way as, you know, when you buy on Amazon, you can pan the phone around your living room and see whether the couch would fit at the same level of overlap. And when in this experiment, we were presenting this stimulus here that was like 3 rods in sort of a triangular arrangement, we were asking them to simply tell us in a perceptual task how deep this object looked like front to back. And then in a second condition, basically, we were asking them to reach and sort of mimic the gesture of picking this object up, like extending their arm behind the mirror and rest their hand at the position and at the distance that they would think the object would be found, was to be found. And so what the data here looks like in a nutshell is basically what you see on the x-axis are normalized scores that essentially express how far the hand was placed in the workspace when they were doing this motor task. And on the y-axis, you see the normalized scores that essentially express how deep that object looked like in the perceptual task. And each one of these dots is basically one person. And so there's 2 things that you want to notice here. Even though the same exact visual imagery was presented to everyone, every person was very internally consistent within themselves, so that if they were reaching at a certain distance, they were also somewhat scaling that impression of depth by some similar distance. And then all of them, you can see that within the sample, there was a lot of inter-individual variability. So lots of different experiences, basically, lots of different subjective experiences. And just to help you read through this data here, this subject that had a score of almost 1, basically, in all the 2 dimensions, it meant that since we presented this object at 2 different distances, near and far from the body, that they were reaching basically exactly a nearly veridical distance of the object. And they were also opening their fingers during the perceptual task as to indicate somewhat of a similar shape. Whereas this other person basically they were overestimating the distance of the object when it was close to the body, and underestimating the distance of the same object when it was farther away from the body. And also they showed biases in the perceptual task that were consistent with this distortion. So they were overestimating the shape of the same object when it was close to the body, and underestimating the shape of the same object when it was farther away. And we called this bias a visual spatial compression, just to indicate that basically there's this tendency to compress the perceptual space towards a certain middle point here. And I'm happy to talk about the possible nature of this attractor here, if you guys are interested. But the point here is that given the same visual imagery, there was a variety of subjective experiences. And so even though at a conscious level, at the population level, they were all subjects were agreeing that they had seen the same stuff, the same object. At the subconscious level, at the behavioral level, at implicit level, if you will, they were responding differently. So that brings us to that brought us to this second question, which is can we actually overcome these kind of biases, given that we saw that we keep on seeing them in perceptual studies, as well as studies that involve the use of virtual reality or augmented reality? Is it something that we can tend to overcome and solve? And actually, there's a lot of problems on this path, because there are technical constraints that are inherent to the virtual reality, to the virtual technology rather, and there's a lot of them. But one of them, which is actually something that Faisal also had mentioned in his introduction before, is this idea of the virtuous accommodation conflict, by which essentially when you are immersed in a virtual environment, or in augmented reality environment, part of your brain is basically making you aware that you are looking at something that, for example, this structure here, as much as it is compelling, you know that it's actually a flat projection, or that comes from a flat surface somewhere. And obviously the head-mounted displays that are more recently being produced, they don't solve this problem either, because they function pretty much in the same way. They're all to some extent, they're all basically modern renditions of Leon Battista Alberti's windows, in a sense. And then again, there are some biomechanical constraints, such as the Virtuous accommodation conflict, that constitute the underpinnings of this conscious bias. And so, in principle, one of the ways that we can try to increase the realism when we use virtual reality technology, and when we do R&E, research and development for getting better and better and more compelling devices, is this idea of trying to make for example, the graphic resolution or any aspect at the level of the engineering development, computer graphics development, such that you can increase basically the amount of the richness in visual, in depth cues, in depth information, to an extent that basically the flatness bias, this conscious bias that you experience by default, is basically compensated the more and more realistic of an imagery you can guarantee, you can render in these displays. And the flip side of this argument is basically that in the real world, because we don't have this flatness, by definition, we don't have a flatness surface that we have, between us and the objects, and we basically, our brain should be attuned to the veridical structure of whatever we are looking at, and essentially no matter the amount of richness in the space around us. If anything, if you enter in a physical room, right, where there's very little amount of depth information, but maybe a dimly lit room or something of that sort, and then maybe you start turning up lights, and you start making accessible more and more information around the space. If anything, your brain and your vision, your perception, your depth perception should become more and more precise, but nevertheless, you should always be attuned to the veridical layout, 3D layout of the world. And that's exactly what we wanted to sort of address in a later experiment, where we really took a very sort of almost a provocative approach, where we just built a very trivial cardboard object, and we placed it in front of the participants, almost in front of their nose. It was about 40 centimeters away from them, so that they could actually reach it, to reach and touch it as well. And we just devised a clever way. Doesn't really matter how, but we devised a clever way to essentially modify the amount of visual information, depth information that was available on the surface of this cardboard object, to basically increase, if you will, increase the realism, or the how compelling that object would look, how better you would be at estimating is in this case the extent of this wedge shape, the front to back extent. And sure enough, here there was no VR involved, there was no AR involved. It was just one person in front of a cardboard object, and nevertheless their perceptual responses kept on scaling essentially with the richness of the available depth information on the surface of that object, and even more so when we asked them to grasp this object, so reach forward and sort of pick it up. Their in-flight grip aperture was also scaling depending on the perceived, essentially the subjective structure of the shape. So it was really compelling evidence that against that argument that realism in VR can only be achieved by increasing the quality, if you want, of the technology, just like that. Clearly, there are some other psychological, subjective biases that we need to take into account when we want to design and improve this technology. So realism in VR displays is not just the whole story. And my point in this presentation is really to sort of raise this talking point here. And lastly, the final example that I wanted to bring here was this final question that we decided to study following these two experiments and others, obviously, in this series, which was okay. So far we had tested visual perception and interaction with virtual environments in the context of a sort of an augmented reality setup. And we found some perturbations, we found some biases. We've also found the same biases with physical objects. Then we asked if, but in both cases, basically the visual imagery was always consistent with the physical structure of the world. So what happens if we perturb the virtual reality environment? Do these biases affect the way in which we adapt to potential perturbation? Because this is really an important question, especially when we're talking about, for example, rehabilitation protocols, as Ryan in the previous presentation was also mentioning. There's a lot of important questions that revolves around this topic here. So very briefly, in this final experiment that we ran, that we published last year, this was entirely in VR, by the way. So you get the whole variety of context, AR, physical objects, and now head-mounted display. And obviously, as you can imagine, participants in this context, they were invited to play darts. And we very nefariously perturbed basically the position of the dart that when they were playing the game. Very frustrating, absolutely. And the task here for them was to sort of learn this perturbation that we had introduced in the computer, in the program, and somehow estimate the distance to the dartboard, so that they could scale that lateral offset to obtain some sort of metric estimate, and so be able to re-aim in the next trial, so to compensate and then finally successfully place that dart in the bullseye, under the assumption that any perturbation in their movement was just purely related to our computer programs and not to any external factor. So we compared two different conditions. in both conditions, the dartboard was at some physical simulated, obviously, distance from the participant, but critically, we had a very realistic scene with all depth cues in it, occlusion, linear perspective, basically a real world environment, pub scene, versus a nondescript environment. So in that case, you were just focusing or converging your eyes on the location of the target. And sure enough, in a nutshell, basically what we found, if you want to focus on the data from at the far distance, it doesn't really matter where we place the dartboard, but really the point here is that at this distance here, the same object, so the same dartboard, was overestimated and was perceived much larger than when they were doing this in the realistic scene, when they were doing this perceptual estimation in the realistic scene, versus when they were doing the same estimation in the nondescript scene. So again, this sort of sanity check of stuff that we had already found in previous experiments. But then we had basically a second condition when we ask participants, so after having experienced this perturbation in a probe trial, to re-aim explicit, so consciously develop some sort of strategy to overcompensate, to compensate for the perturbation, which implied that they had to sort of calculate this angular offset. And we also had another implicit condition, which I'm not going to talk about, but I can talk about during the Q&A if you guys are interested. The core take-home message of this experiment here is really that when participants were consciously re-aiming, basically what we found is that the amount of compensation was larger when they were playing in the pub relative to when they were doing the same game in the nondescript environment. And so these are metrics that are basically measuring this bias between the two conditions. This one is particularly telling, I think, because it basically means that participants, when they were shooting, which, by the way, shooting was done by translating a controller in space. Imagine there was the HTC controller. They were mimicking basically kind of like a slingshot type of movement with the hand. When they were playing this game in the realistic scene, participants were showing a higher acceleration peak, which was also earlier in time. So basically, they were reacting faster and giving a higher speed, basically importing a higher speed to their movements, which is essentially consistent with this idea that it's exactly the pattern of kinematics that you would expect if someone tried to essentially shoot at something that looks farther away. So the reason why we had found this perceptual bias, this increase in perceived size, was because they thought that in the pub, the dartboard was basically farther away from them. And so they were rescaling the whole scene accordingly, essentially. So there we go. So we have tried, making assessment over the course of several years with augmented reality, with virtual reality, and even with trivial simple objects. And we've consistently found so far a certain level of subjective experiences that don't really seem to be related to how much realistic the scene is in this simulated environment. So my personal take on this, and I don't want you to walk away with the idea that I'm actually a critic of the VR technology or anything like that, because I mean, quite the opposite. I'm quite a fervent advocate of VR, AR, and XR, and I do think that they actually offer a very powerful opportunity for, on the one hand, in my personal view, to study human depth perception. And this is why I'm flagging this as a nerd alert, because I'm aware, I'm conscious that this is a very academic, ambition of mine. But it's just, if you consider the potential that this technology has in society, it's just enormous and very important. It can really make a significant change, as I'm pretty sure everybody here would agree with. But it is also the case, this is my argument here, that it's not only, we don't just need to see, to tackle the problem of realism in VR as a purely as an engineering problem, because the data and the evidence shows us that even when you can get a realistic environment as much as the physical world itself, you still have these problems that I mean, you still have these perceptual distortions rather that we need to take into account. And so in addition to that, you know, trying to aspiring to just having more and more, say, computer power is also a slippery road in my opinion, because I'm not sure that it might be sustainable in the long run, you know. So as we explore the ways to improve this technology, we have actually an opportunity to get a better understanding of how humans interact with the environment. And so this is really a challenge and an important, so developing VR and AR is really an opportunity for us to understand human nature itself. Okay, so with that, I'm at the end.
Thank you, Carlo. That's a really fascinating talk again. Thank you. So it was great to sort of hear you give the same disclaimer that I did. Is that, look, we don't hate VR.
Yeah.
This is what it takes to sort of, when you take a critical eye and you sort of step back and you look at the evidence and you think this through properly, what is and what isn't required in these sort of development of these systems. So that's really, really fascinating. The fact that you had your people, your participants in a pub playing darts makes me question, well, there's a few questions I can come up with, but I have only time for one. So I'll ask you, if that person was Phil the Power Taylor, professional darts champion, I don't know, world champion for however many years, how might that response change? Would it be amplified or would it be sort of attenuated?
Yeah, this is a very fun one, because I've actually, anecdotally really, not systematically, but I've actually analyzed that to the extent that just because a couple of my participants in that particular study, and actually in the study also with the AR, the first one that I presented, some, you know, obviously the population was university students, and some of them were in sports teams, you know. There was a baseball player at some point, and there was another one that I forgot exactly what they were doing. But the point is that the particular sport that they were doing was one that required sort of a training in depth. You know, baseball, you need to do many times some this sort of catching behaviors or interceptive behaviors that require a very fine estimation of distance and depth, and, you know, radial expansions of the visual, the optic flow and stuff like that. And actually in those particular subjects, the accuracy was somewhat of an overlay, was somewhat of an overlier towards veridicality, to the extent that actually I remember this quite specifically, the baseball player, because he knocked out the machinery, the apparatus that was behind the mirror in the AR system. So we had to interrupt that session at some point, because it was so accurate that it basically pushed everything away. So there's a component that has to do with the experience and training, and I think the important aspect of it, which I didn't talk here, but obviously is an important factor when we talk about interacting in the environment, and actually in a virtual environment, of course, is that we not only do we have, you know, the eyes, as I was talking at the beginning, but we also have, you know, a body. So we touch things, and we actually have some ways to calibrate our perception to some sort of ground truth. So there is this component that is actually one of the things that I have in a pipeline, let's say, for future experiments, just to see how the proprioception is integrated with visual perception.
Yeah, that's really interesting, Carlo. Thank you. It reminds me of some well-known sort of research on something called e-special skills, which I'm sure you know about. The specificity of sort of skill is sort of shown in sort of basketball players, for example. If you look at their success rates at the free throw line, far superior to anywhere else on the court because they just practice that so often. And I just wonder about sort of a darts player specifically within that particular distance. That particular sort of action, if you were to mimic that, what we would get. So the other part of your talk, the sort of second half actually dovetails really nicely with the next two talks that we have from the computer science sort of colleagues. And it's really a sort of challenge and sort of a provocation really to say, hey, look, we don't need to get realism, perfect sort of realism, or attempt to sort of get perfect realism through sort of increasing computational power. So maybe there are smarter ways of sort of improving the development of these systems. And I think sort of our next two speakers will build on that when they talk about sort of the algorithms that they're developing. So with that, thank you, Carlo. I will next introduce Markus. Hello, Markus. So Markus is a computer scientist who's working on exactly these sort of challenges that sort of Carlo has sort of described. And Markus has a very interesting sort of career. He's worked in industry. He's been a sort of a PhD student at sort of was it Chalmers University, Markus? Correct me if I'm wrong. Has worked at the Bosch Research Center in Palo Alto, and has a sort of wealth of experience on some of the technical sort of issues. So Carlo and Ryan have talked about the sort of human engagement. And now Markus is going to talk to us about sort of the challenges from a computational sort of perspective, and how his work on sort of algorithm development for sort of GPUs is sort of supporting the development of sort of next generation systems. So Markus also has, by far and away, the most immersive presentation that he's in his presentation. So that's really cool, Markus. Thank you. I'm going to have to learn how to do that. So I will hand over to you now. Thank you.
Yeah, okay. Yeah, thanks for the short introduction. So as mentioned, I'm Markus. I'm a lecturer at the School of Computing here in Leeds. I've been doing computer graphics for quite a while, so I started with my PhD in real-time rendering, subset of computer graphics, and have been working with rendering GPUs for a long time, well, almost since the PhD. So in a short sentence, my work is more about how we put things on the screen or into a VR headset, not as much what we do or what we put in there. So I'm happy to leave that to people who study interaction, vision, and content. But brief introduction. So I'm not the only one doing computer graphics here at Leeds. We have a group on visualization and computer graphics. You can see the guys there. Some photos, including mine, are slightly out of date. But with the 5 members of staff that we have, and all the PhD students that are involved, we kind of cover a wide range of topics in these subjects from a computing perspective. So obviously, there's VR, perception, and interaction. The topics are roughly listed in the order you see the people from top to down. So that's mainly Rafael, who is the next speaker here as well. We have people looking at simulation, vision, and machine learning, again from a computer science perspective. Looking at visualization together with human-computer interaction, and also visualization in terms of large data structures. So how do you deal with data that is, well, too large to have on a single machine, or even too large to look at in a human time. And finally, myself, who is specializing in real-time rendering. I'll get into that in a moment. And kind of the algorithms and data structures that allow us to render at the speed and quality that we do these days. So just to make sure that everybody is on the same page, I'll start from the bottom. So I've used the word rendering already, and this is just a term that we use when we are drawing something, typically on the screen, but we might be rendering to images, or in this case, I have a program that is rendering me onto the video feed that you see. So general process of drawing stuff. Now, in computer graphics, this all involves quite a few different things. So on one hand, obviously, there's the programming aspect where we have to implement this somehow. And here we rely on algorithms that have been developed over the past few decades into data structures that allow us to manage the stuff that we have in our scenes and that we want to show efficiently. There's a bit of physics, so we need to understand how light interacts with the world so that we can simulate this. There's an example here on the bottom from my old group at Chalmers. Basically, this is for a film where we want to insert some cars into a rendering. We can see a lot of physical effects. So these cars cast shadows. They have lights that illuminate the surroundings. We have light going through glass and all this kind of stuff. Now, this also involves some amount of math just to express and describe these systems that we're trying to solve. And finally, of course, I think most people are aware of these things. We have the graphics cards, which, well, I don't know if everybody has seen one outside of the computer. Usually these are inside of your computer. And that's where a lot of our, software runs. So graphics cards, they have a lot of very specialized cores that we can use to do the vast amount of computations that we need to do to just display a single image. And to look at or give you an idea of what it takes to render a single image, I briefly searched for a picture of a screen online. You can see here next to me. This particular screen has a resolution of 2,560 pixels times 1080 pixels. If you multiply this out, you get roughly 2.5 million pixels. If you want to show an image on the screen, we basically have to compute the color for each one of these pixels. It's a bit of an odd screen, so I listed a couple of other common resolutions. Fake HD, popular if you want to make your stuff run faster, but not really used these days. Full HD, probably the most common one still. So if you have a normal screen on your in the office or on your desk, you probably have this resolution. It's roughly 2 million pixels. That's easy to remember. And if you go to 4K, well, it's almost 4K times 2,000 pixels. And we have a total of 8.3 million pixels. Now, from a computer graphics programmer point of view, this just gets worse and worse because we have more and more pixels that we need to compute, maybe not more resources to do so. And the situation gets worse in VR. This is a sort of old headset from 2015, one of the first commercial ones, and it already has 2.6 million pixels. So it has two screens, one for each eye, twice the work already, but each eye has a fairly high resolution. I'm including this old headset mainly because I want to show this picture, this really great picture about VR. We've all looked that way at some point in our lives. This one is. More modern headsets have higher resolutions. We need those higher resolutions to be able to show good quality images. If you had one of these older headsets from this generation of headsets still on and had something that was trying to show text, it's typically very difficult to read. And even with the Valve index, I think it's still difficult to show scenes that have this kind of very detailed stuff. So text somewhere, you need to scale up the text massively to make it readable. But then, on the other hand, as we're pushing for higher resolutions, we get again more pixels, which we need to somehow draw, and that causes kinds of problems. This is on the right-hand side, you can see Pimax 8K, which basically has two 4K displays glued to your head for a total of around 16 million pixels. The first generation of these had problems just transferring this amount of pixels from the computer to the headset. So the images that you would send to it were lower, I think half of the resolution. Now in the very newest iterations with the new standards, so new DisplayPort and HDMI standards, you can push this amount of pixels. If you've ever wondered why you sometimes need to buy a new HDMI or DisplayPort cable, despite it looking the same, there are some internal changes that allow you to achieve those higher transfer rates more, with less errors. We already discussed this a little bit, I think, in the first talk. So this high resolution is not the only problem that we have. Other aspect is the frame rates. So at the rate we show images, and we have to show images that change a little bit to create an illusion of animation. And now, long time ago, TV movies used to be maybe 30 images per second. Old gaming consoles used to also aim for that. But nowadays, for normal screens, we're mostly aiming at 60 hertz or 60 frames per second, so 60 images per second. If you go a little bit more fancy with a gaming screen, you might end up at 120 hertz, 240 hertz, and so on. But yeah, that's, I mean, it's getting standard, but it's a little bit specialized. For VR, you really want these higher frame rates, as they tend to be much more comfortable to view. Older headsets, so even in 2014 and in the development versions before that, they were aiming for 90 frames per second, from what I remember. These days, you probably want to aim for 120 frames per second. So just to give an idea, that leaves less than 8 milliseconds to compute each image. So 120 images per second. If you don't have a VR headset but are a little bit into gaming, maybe you've seen that there are high resolution screens also available, 4K screens that can run at these high frame rates. But if you want to drive one of these screens for a recent game or something at these frame rates, you need relatively good hardware. And the same holds true for VR, of course. So a little bit of another aspect of this. On a normal screen in a game or something, or some other application, if we drop a frame, okay, this is annoying to the user, maybe people will notice it. But in VR, it's considered much worse. Again, much more noticeable, also from this cybersecurity aspect. Another problem people are struggling with is HMDs, headband displays. They go on your head. For these very high resolution headsets, so the ones that I showed before, we need a tether to the computer. So you have a cable going from your head to the computer. It's difficult to move around and you can get tangled into this. Now, of course, there are HMDs that try to work around this by including essentially the computer in the headset. But at that point, you're looking at mobile phone hardware, maybe a bit more modern than what I have, to do all of the work instead of one of these cards. Yeah, this one is going to be less powerful than this one. But on the other hand, we'd really like to have a small form factor that uses less power so that we can have these experiences where we can move around more freely without the cables, and also maybe don't need a full-blown gaming computer to drive your VR experience. So George, I mean, in VR, compared to normal rendering, we tend to have more pixels, higher frame rates, and it's worse if we mess up stuff, if we miss frames or have similar problems. What can we do about this? I'll give a very short overview of some of the approaches, detail it a little bit. I mean, obviously, one answer is better hardware, but if you've recently looked at buying a GPU, you know that prices have been, they've been going down a little bit, but now they're slanted to go up with the newest generation. They're getting quite power hungry as well. Other solution is better methods, so better algorithms, better software, better data structures that allow us to render more with the same hardware. And I put cheat in parentheses because in computer graphics, we like to cheat a lot. Games are even worse. And the idea is if you can't see something, why even try to show it? Yeah. And one example that I have here of getting these better methods is the real-time ray tracing we saw being released a couple of years ago. That's the consumer-facing side. Nvidia Rtx builds on a decade or more of research into ray tracing on GPUs, improving hardware, improving methods, all to enable this a few years ago when they first released the hardware, and it's been improving. If you know where to look for, one of the conferences, high performance graphics, you can find papers from people working at Nvidia and also other researchers publishing in this topic of ray tracing 10, 15 years ago. And maybe they were clued in, but most of us didn't know that they were planning to actually put it into hardware at that point. So let's look, but yeah, this is for the methods part. Let's look at what we can see when we render for a VR headset. So obviously, I already mentioned that we need to render 2 images, one for each eye. I've included a screenshot here. This is actually from a master thesis of a student that I was supervising some time ago. And he's just showing the 2 images that he rendered before sending them to the headset. If you look at them, they're quite similar. You see roughly the same thing. The images are a little bit shifted, but that's to be expected. After all, our eyes are a little bit shifted next to each other. So if you focus on this aspect, there's an example here. You can find a lot of these points where we have the same point in both images. I've highlighted one of these. So one thing that one might be able to do is try to share work between those 2 points. So when we try to render an image, when we try to determine the color of one of these pixels in the image, we have to do some computations. We have to find what is shown in this pixel. Then we have to compute what shading it receives. It's basically what kind of material it has, what light it receives, and how this light is reflected to the eye. Now this point is a point in 3D space. We're looking at the same point. So if we can find out this correspondence, that 2 pixels, 2 different pixels are looking at the same point, maybe we can reuse some of the computations that we do when determining the color of this point. For example, well, because they are the same point, they will receive the same amount of light from all of the surrounding light sources. There is a bit of tricky stuff here. We cannot just simply compute the color and then share this. Although again, as mentioned before, some people are cheating and they do this, especially in games. But if you imagine a very reflective object, you can, well, kind of construct an example where the eyes don't see the same thing. So if we were to compute the same color, well, that would be kind of giving the wrong answer because it changes between the eyes. Now there's a couple of different approaches to this. The simplest one is reprojection. That was when I was saying that a lot of people like to cheat here. So basically you just roll one image and then you say, well, most of the other image is going to be the same. So we just take parts of this one image and put them into the other image where they roughly belong. You end up with some holes, but you can try to fill in those. But this gets a little bit tricky if you have differences. So if you have these very reflective or specular objects, well, the result isn't quite correct anymore. Maybe, well, you can say that people will notice it, so you can get away with doing it anyway, depending on the scene and so on. You might want to go for something better. So what you could instead try is to, as mentioned, share some of these computations. So if you can figure out that a certain point is visible in both images, you can try to figure out the light that this point receives, and maybe remember that, and then just do calculate the light that is reflected towards the eyes separately still. This is a bit more tricky to do, a bit more costly to implement, but yeah, we've been trying to do stuff like that. So the example that I showed before, these first steps from the master's project of the student, Mick van Gelderen, try to do this. So this is based on a technology or on a method that I published some time ago, where we try to handle the case where I have seen many light sources. So in this case, each of these kind of colorful dots is a light source. This is, by the way, what we refer to as programmer art. It has a purpose, but it's maybe not the most well-designed artistic scene. But each of these points emits light, and what we try to do is then figure out which light sources affect a certain point. And this will be the same for both images. Then we remember this, and when we compute the final color, we can use this information to then determine the reflection towards the eye. There's more to be done here, but it's a nice first step. And of course, one doesn't have to just stick with one of these approaches, we can try to combine them. So maybe we can look at the image and figure out, okay, this part of the image wasn't very reflective, so we can just take the results from the left eye and put them into the right eye. And for parts of maybe more reflective, we need to do more computations. There's a lot of variations here. Transparent objects, you see through them, they don't have a single color. Okay, those are difficult. Those are difficult anyway in computer graphics, and so on. There's more to be done in that direction as well. And in fact, well, even on single screens, we can use some of these ideas. Now, we've said that the left and the right image are kind of similar when we compute them, but that's also true for an image and the following one. The time step is tiny, so 8 milliseconds, 16 milliseconds, 30 milliseconds. If not too much changes, we can take one image and kind of project it forward in time, and then apply the same ideas there. Of course, if we have a VR headset, we might be able to do both forward and left to right, or share data between the screen images. The other point that I had mentioned is just looking at human vision. So, well, human vision isn't perfect. All of us with glasses know this, but I think Rafael will take over in his talk and explain a little bit how he plans to exploit this and how essentially he cheats in reducing the computations to almost half of the work, I think. So I'll hand over to him for the next talk. Oops. Well, I'll stay here in case there are questions.
Thank you, Markus. That's really great. So yeah, you've already done the handover to Rafael. It's seamless. I love the way that this is all transitioning. That's brilliant. So yes, I think, I mean, this is also turning into a networking event now, because I think you and Carlo should definitely talk, and I think Rafael as well, about the sort of perceptual side. I think Ryan, in terms of the action, where sort of we always think of perception action as this sort of loop, and that seems an important part here if you're thinking about where efficiencies can be sort of made. How do people interact with those environments? So that's really fantastic. Thank you. So we will, in the interest of time, skip straight over to Rafael and hand over to him, and then he will wrap this all up. I think he's going to close the loop, so to speak, and talk about how he does half the work as Markus, I think, is the claim there, right? Work smarter, not harder, right? So Rafael, go ahead and tell us.
Let's see if you live up to the promise.
Okay, well, I'll do my best. Yeah, thanks for the handover introduction. Hi, everyone. Thank you for coming. Thank you for staying until now. I think my talk will be a little bit shorter. I have one project that I want to talk to you guys about. So my name is Rafael. At the same group as Markus, as you've seen my photo on his slides. Also lectured at the University of Leeds since last year. So about me, Leeds, DCG group. I am originally from Brazil. I've worked on several different topics. I've moved around a lot. I worked on video-based rendering, point clouds, 3D capture, and using VR, AR systems for dance while I was in my PhD in Portugal. I worked with tools for the entertainment industry, XR teleconferencing when I was at Victoria University of Wellington, New Zealand. Previously, I was at UCL working on graphics pipelines for VR, AR, the topic of foveated rendering, looking at new display technologies, and my current focus is continuing most of the above, but mostly exploring perception, graphics, trying to improve user experience in VR using computer graphics techniques, and also looking at 3D reconstruction and putting that in VR. Right, so just looping back, because we had 3 talks, Faisal talked about virtual reality being something that actually around the 90s was already around. This is the iPhone, which was maybe one of the first times, like a first public demo of what we would nowadays look and identify as a VR system. And it was a big thing back then. But you can see, well, if you can see I'll just get a laser pointer. You can see my cursor here. We have some hand tracking devices, lots of cables going around, and the graphics weren't very fancy back then, but you could communicate. And the idea was having some sort of virtual conversation with someone. But everyone probably know about the book or watch one of the movies that came out about VR. Ready Player One is that idea of you put on this device and you're completely immersed. Your vision, your movements are recognized. You can see everything. You can feel everything. That's kind of where I think the holy grail would be, is this kind of experience, right? Looking at the definition that you find on VRS.org, is that virtual reality is a term described to use a three-dimensional computer-generated environment which can be explored and interacted with by a person. And the main idea is immersion, right? And I think we've heard a little bit about this in the previous talks already, and how difficult it is to achieve that level of immersion. Well, some of you that are into games or Nintendo fans might remember the Virtual Boy from '95, which was maybe a more out there commercial product. You had Super Mario games in it, and that's how you used to play the Virtual Boy, at least the commercial version, top of your desk. Not very good posture you needed to use. You couldn't move around. You had a controller connected to it, and eventually you had some arcades that, well, after the pandemic, wouldn't be very safe to put your heads in there. And yeah, and graphics-wise, you had even limited colors that you could output. Why did we stop seeing these kind of displays back then? So Faisal showed that graph that eventually a boom happening. So we just started hearing again from commercial virtual reality headsets more recently. Well, back then they were not very portable, expensive, poor display quality, so worse than playing games on TV, nausea and headaches, and maybe neck pain and back pain from playing in this position. Well, compute power, Markus talked about this. We've got loads more now. Screens are better. They're smaller. We have higher refresh rate on our screens. And perhaps the most importantly, we have better sensors and systems, right? So while on the Virtual Boy, you had your head right there, we have a lot better sensors to figure out where our head is and have accurate head tracking. Systems to render the images faster, to transfer the images to our headsets faster. But is it enough? Well, our computers are fast, our screens are sharp, they refresh super fast. We can tell where the head is very quickly and accurately. We have super fast USB network for transmission. So what's holding it back? Well, looking again at the VR rendering process in a bit more detail, what exactly happens? So the computer will look at get information from the headset and find where the head is currently at. So you're looking, let's say, straight ahead. The computer will start generating an image. While the computer is generating an image, you move your head a little bit, and when rendering finishes, you get an image from where your head was looking at maybe a few milliseconds ago. If you move your head fast enough and you do this enough times, your user will feel sick. One of the reasons is, well, it feels like you're drunk, right? So the image lagging behind is not moving. It's not matching your balance, the balance your body feels with what you're seeing. Eventually, you end up feeling sick. And like we heard a few talks ago, quality requirements won't stop increasing, right? And this is a funny thing that we always look at maybe video games or movies that we watched maybe 10 years ago. We think they were completely realistic. This is real life happening right in front of my eyes. And then when we look at them now, they look really bad. The special effects are really, really poor. You can really see that that's poor CGI. And because, well, the quality keeps increasing, we get more and more realistic scenarios. This is from Unreal 5, a game engine that is very, very recently being released. And the quality of the graphics you get, the quality of the shadows, the movement is really out there. And it takes more computing power to achieve this quality, and expectations of people also are raised. So in a sense, computer graphics is both the villain and the hero, because in one sense, we're generating these beautiful images and getting people's expectations super high. On the other hand, we can do research like Markus was mentioning to make things faster and deliver this to people. and deliver it in VR. Like Markus said, we had 2 screens and our heads moving, so it's a bigger challenge. Right, so what are possible solutions to this? I will talk about one of them, which is foveated rendering. So what if we know where people are looking when we have VR experience? Because some of the latest head-mounted displays have eye tracking. What kind of cheats can we use? And it's non-derogatory term because it's really cheating. When we get there, you'll understand. Right, so a little bit about how our eyes work. We have a different distribution of photoreceptors in our eyes, cones and rods, and in general, they have this different distribution, and I won't get into detail of what each one of them means because it's not particularly relevant for this talk, but you can see that in an angle, look at the center of your eyes. If you look at an angle deviating from the center, this is the distribution, right? So you have less and less receptors as you go to the periphery, but not only less receptors, but the way our brain interprets things changes as well. So things are aggregated, and this is some findings that we'll get into. I'll show a few of the references of this, but our brain actually not only sees a less sharp image, but it groups things together in the periphery. I have a few examples. So this is an actual, a very good example from a paper that shows if you focus right here where my pointer is, there's a little O there. This is a representation of how all of these letters are the exact size that allow you to actually see them in your peripheral vision when you're focusing on the O. If they were a little bit different, or a little bit smaller, you probably wouldn't be able to discern them. So that has to do with the loss of acuity that you have. But then the pooling and the grouping, this is a great example. If you focus on the where my mouse is, if you look at your screen right here, you can probably tell every single element in the periphery very clearly. But when you focus here on this X and you try to discern what's happening at the center where you were looking for, it's a lot harder because your brain is aggregating these 3 letters, and it becomes harder for you to discern. Especially if you look here again and you try now to discern what's at your lower right, so the K plus, it becomes difficult as well. So that's the effect people call visual crowding, right? So we're going to take advantage of this. Because we know where people are looking and we know how the brain works, let's try to just render where they're looking and try to generate an image that produces the same response in the brain, in the periphery, but that is a lot cheaper to calculate. This is an exaggerated example. We'll get into a few more realistic, but if you follow the red dot, which represents where the person was looking, that's the only part that we actually need to generate an accurate image. This is some work made with that I worked on with some colleagues from UCL last year. So this is the original image. Look at the center of it, and keep looking at my cursor. This is the idea. While you're looking at the cursor, it should produce a similar response. In this case, it's a little bit exaggerated, but you get the idea. This image here was very cheap to compute because it's not very sharp, but it does the job. Sorry. This is what we call metamers. Metamers are similar stimuli that by our human visual system are detected as the same. Image metamers, or ventral metamers, are 2 images that when you're looking, if you look at a certain point, you also can tell that there's something distorted. In this case, when looking at the red dots, everything in the periphery feels like text. And this is a really amazing work from Freeman and Simoncelli in 2011 that show that you can actually do this. And they are the ones that talked about the pooling effects in our vision. So we want to improve the previous foveated rendering techniques, which would just make it less sharp, but considering now the statistical effect that it has. So our goal was, instead of generating those metamers in 6 hours from 3 Celli, can we actually do it in 10 milliseconds? An overview of the process can be seen here. I think with the compression from Zoom, it's not very clear, but we look at oriented responses at different scales in the image and calculate statistics, because the theory is that our brain will look at different orientations, different frequencies, different scales, and will aggregate that information that is similar. And then we simply apply those statistics to noise and generate an image. So if you look at the traffic lights, these are examples that I generated to be more adjusted to this type of screen. If you look at the lights, the periphery should look okay. Now, if you look at this plant, the periphery should also look okay, even though it doesn't look okay when you look directly at it. I didn't include a tracked demo because of well, the compression of the video, so we just had images this time. We did a user study where we saw that people could recognize, distinguish between the C and the O a lot better than when they were blurred, comparable to the actual image. Preference between the 3 Celli metamers and our metamers that were fast found to be very similar. And our image and 3 Cellis were both seen as very consistent with original images, non-distorted ones. Can also be used for compression of images without loss, can be used for texturing, can be used for path tracing as well. Those are all non-VR applications. What are the impacts for specifically VR applications? First, this allows us to have bigger displays and faster headsets, because we just need to worry about a very particularly small part of the screen. If we understand vision, we can battle sickness as well. People get sick because what they see doesn't match the rest of their senses. We can actually try to improve that if we know where they're looking and we understand the eyes and understand cognition, as we heard with previous talks. And also, if we make things faster, if we generate the images faster, not necessarily higher quality, but just generate them faster, we have extra cycles to compute and represent one's body in VR accurately. So what would be the impact of having actual accurate body representation in VR? That's something that I'm very interested in looking for. And that's it. Thank you very much for staying to the end. And yeah, any questions, just post in the chat.
Brilliant. Thank you very much, Rafael. That was a really fantastic and great way to end this with sort of potential solutions to some of the issues that have been sort of highlighted for, in fact, a number of years now. In fact, yeah, right back to sort of the very beginning of commercial VR. So foveated rendering being this sort of dream solution. So that is, I think that wraps up the talks. We are slightly over time, so our apologies for that, but we really appreciate you all sticking to the end and for taking the time out of your Friday evening to come and listen to us. If you have any questions, perhaps you can't think of them now, or maybe they sort of pop up to you sort of later on, and you think actually sort of at some point in the future you think, oh wow, I'd really love to sort of talk to these guys about this a bit more. I will share our email details with you over Eventbrite by messaging you with our information on how to contact us. So feel free to sort of reach out. If there's anybody, if you want to hang around here and have some questions, then feel free. I will still be around for a few more minutes. Otherwise, thank you very much, and enjoy the rest of your evening. Thank you.
Thank you, Faisal.
Yeah. Thanks, everyone. Thanks, Joanna. Thank you, Valeria. Thanks, everyone. Bye. This is the best part, when you see all the thank yous sort of flowing through. So guys, I don't know if I've connected you all before, Carlo, Ryan, if I've put you in touch with Rafael and Markus, but if, I think you guys should definitely have a chat.
Rafael, I just want to say very, very quickly, the foveating thing, it really reminds, I'm sure you're familiar with the Diorama effect in photography.
I'm not sure. I'm not really connecting the dots.
No, yeah, it's basically a technique that's used in photography to basically render, like when you take a picture of, like, say, a miniature scene.
Oh, okay.
If you adjust the blur in a certain way, basically such that you limit it to the very center of the focal point, but then you dramatically amplify it in the periphery.
Yeah.
You get this impression of that the scene immediately appears like it's real. Like, instead of being a miniature thing, it appears like it's something that is in the real world. So that was really it reminded me basically of the same principle what you presented.
Main goal was to create an illusion, right? And if you're around the university, I have this running on headset, so you can come and check. It actually works. So we have actually, so the paper was describing how this, in a practical system, you could have this as remote rendering, right? You could calculate the statistics and just send the statistics, and someone else would just very fast generate the images. We have a proof of concept. We don't have two computers sending things, but it runs super fast. So it's all in one computer. You can come and check. I have two versions, one running with eye tracking and one running on the Pimax, so you got a larger periphery. It looks pretty cool.
No, totally. I'll get in touch for sure.
Yeah, it looks like Mary, who's in our audience, I don't know if she has a mic available, is also aware of this sort of issue from a film photography perspective as well. Very interesting. Thank you, Mary. I'm not sure where you're at, where you work at, but if you'd like to come and sort of learn a bit more, try out some of our sort of kit, feel free to get in touch. Great. Okay. And Markus, I think we were all envious of your setup. Inspired that the next time we do a public sort of talk, we will have to do it your way. So I think you have to give us some tutorials on that. So thanks for that. I think we'll wrap it up over here and let everybody sort of head off for their evenings. And I will put this recording up on YouTube in the next sort of few days or so, and I'll share the link for you all. So thanks again. Thanks everyone for your time. Thank you to the speakers. All the best. Okay.
Yep. Thanks for the invitation.
Bye, everyone.
And have a good evening.
Bye.